Alright kiddos, welcome back. And today we're going to talk about spontaneous chemical reactions. Now first of all, let's talk about what spontaneous is. It's any physical or chemical change that once begun occurs with no outside intervention. So any physical or chemical change that once started will occur without me having to continue to add energy to it. For instance, you've all lit a Bunsen burner in my class. Once you start the Bunsen burner, once you ignite the methane, the combustion reaction starts. Do you have to continue to add a match or to continue to light that burner for it to burn? No. Once it was started, you don't have to continually add energy for that process to go on. Now, non-spontaneous reactions, you would have to continually add energy for the process to continue, and we'll talk about some of those. Now, first of all, let's talk about how nature proceeds spontaneously. So nature goes in two directions spontaneously. Nature goes to an area of lower enthalpy. So we have a negative delta H. Nature prefers exothermic reactions where they like to go from a high energy situation to a low energy situation. Imagine a mountain biker. Here is this mountain biker. Obviously, he's going downhill. Once he started, right, once he began going down the hill, did he have to continue to pedal? No, he went downhill spontaneously. Once that change began, once he started going downhill, it continued without any outside intervention. Now, what if we wanted to look at a non-spontaneous example of this bicycle rider? So let's say he wanted to go uphill. So he pushes off and he begins to go uphill. Will he spontaneously go uphill without continuing to add energy? No, of course not. It's ridiculous, isn't it? The same thing is true with chemical reactions. Nature prefers to go to lower enthalpy. It prefers a negative delta H. We call those exothermic reactions. Okay? Now, the other direction nature prefers to go spontaneously is to a degree of higher entropy. So you might be saying to yourself, Hummer, I've never heard of the word entropy before. What is entropy? Well, entropy is the degree of disorder in a system. So if I wanted to define entropy, I would say the degree of disorder in a system. So nature goes to a higher entropy. Now the symbol for entropy is S. So the change in entropy is positive. Nature prefers a positive entropy. That means nature will continue to move in a direction where the system becomes more and more disordered spontaneously. Here, let me give you a simple example. This is actually a picture of my sock drawer. You'll notice that my socks in my drawer at one time were neatly organized. They're all folded. I have the light colored socks here on the left and the cream colored socks here towards the middle, and then the browns, and then the blues, and then the blacks. I have a nice orderly system. Everything is in order. Did it become that way spontaneously? Of course it didn't. In order for my sock drawer to look that way, I had to put in a lot of energy. In fact, in order to maintain that order, I have to continually add energy. Now, let me show you what my sock drawer normally looks like. Probably a lot like yours. Some socks are unfolded. The short socks are mixed with the longer socks. The white socks are mixed with the darker colored socks, it's chaos. This happens spontaneously. This is a positive entropy, a positive change in disorder. And that's the way nature moves. Do I have to continually add energy to get my sock drawer to look like this? Of course not. It does so spontaneously. And the same thing is true with chemical reactions. Chemical reactions tend to go from an ordered state to a disordered state more spontaneously. In other words, if I have a perfect crystalline solid, you guys know that solids have a high degree of order. Well, nature would proceed in a direction to disrupt that disorder, for those solid particles to become liquid particles where there's more disorder, and for those liquid particles to become gaseous particles where there's even more disorder. So, the tendency towards increased entropy is summarized in something called the Second Law of Thermodynamics, which states that spontaneous processes always proceed in such a way that the entropy of the universe increases. Entropy is sometimes considered to be a measure of the disorder or randomness of the particles that make up a system. Particles that are more spread out are said to be more disordered, causing the system to have a greater entropy than when the particles are close together. Now recall that the change in enthalpy, delta H for a reaction, is equal to the enthalpy of the products minus the enthalpy of the reactants. Do you remember Hess's law? Yeah, we just finished with that. Well, the change in entropy for a system can be calculated similarly. We can take the entropy of the products, subtract out the degree of entropy in my reactants, and I will have the change in entropy for the system. So it's a version of Hess's law, but instead of measuring enthalpy, we're measuring entropy. And you will see there are some data tables that will actually list the entropy or randomness of certain substances at what we call standard thermodynamic temperature and pressure, which is 0 degrees Celsius, which is 25 degrees Celsius and 1 atmosphere of pressure. So if we take a look at this picture here, look at how organized a solid is. And then look at my liquid. The same number of particles, but they're not organized. They're spread out. There's a degree of disorder that is increased. So we say that the entropy going in this direction is positive. It's greater than 0. What about from a liquid to a gas? When I go in this direction, boy, entropy is increased even more. So when I go from a liquid to a gas, entropy also increases. Now, when I go in the other direction, we can see a decrease in entropy, which is not spontaneous. It requires some energy to be put into the system in order to get that increase in orderliness. So if I were to go from a gas to a liquid now, that entropy sign would be less than 0, negative. And if I were to go from a liquid and become even more ordered as a solid, that would also have a negative entropy value. So let's try some. Let's see if we can predict just the sign of entropy change for each of the following changes. So I'm going to do letter A for you, and then I want you to pause the video to see if you can do the rest of the problems without my help. Okay? All right, so letter A, it looks like we have ClF gas and F2 gas creating ClF3. I have 2 moles of gas on the reactant side, and I'm creating 1 mole of gas on the product side. Don't you think 1 mole of gas would be more ordered or less disordered than 2 moles of gas? Yeah, it would be. So here we would say that delta S has a negative sign because we are becoming less disordered. Remember, entropy is the degree of disorder in a system. So when orderliness increases, entropy sign is negative. Try to remember that. Okay, you do B, C, and D, pause the video, come up with a sign, either positive or negative, for those, and we'll see how you did in a second. Okay? All right, welcome back. Letter B. Looks like we have ammonia gas, and we're taking that gas and we are dissolving it in water. Yeah, here we would end up with a increase in entropy because now we're going from a gas to these particles being dissolved by water. There's water molecules now that are introduced into the system, and they're getting between the ammonia molecules, and entropy in that system would be increasing. Well, if you got the letter B right, you probably got letter C right. Here we're going from a liquid to something dissolved in water. So once again, we would expect the entropy, the degree of disorder in that system, to also increase. All right, how about letter D? Here we're going from C10H8 in the liquid phase. So we have something like this right here, and we're going to C10H8 in the solid phase. So we're going from a liquid to a solid. Well, it looks like the solid's much more ordered, doesn't it? So the degree of disorder in the system is decreasing in letter D. Okay, we'll practice a few more of these in class. Trust me, it's not too horribly difficult. I think you guys will get the hang of it quickly. Now, we're going to end the video soon, but I want to introduce the question that we're going to try to answer in the next video. Does ice melt spontaneously? Now you might think, Hummer, that's a silly question. I take an ice cube out of the freezer, I put it on the countertop, and voila, it melts. I don't have to continually add energy for that ice cube to melt. Well, that's true. At room temperature, you don't. But what about at temperatures below 0 degrees Celsius? Yeah, the ice cube's not going to melt spontaneously. So sometimes temperature will play a role in the spontaneity of a reaction. So we're going to talk about that next time. See you soon. Bye-bye.